Bom, boa tarde a todos, bem-vindos à defesa da tese de doutorado da Nicolle Miranda de Lima. Eu peço aos alunos que estejam presentes na defesa e queiram contabilizar a presença no seminário, por favor, coloquem no chat o nome e a matrícula, para a gente poder contabilizar a presença de vocês. Tá? A tese será defendida em inglês, então vou começar a falar em inglês a partir de agora. So, good afternoon, everyone. Welcome to the PhD thesis defense of Nicolle Miranda de Lima. I thank already the evaluation committee that's composed of Professor Vladimir Alvarado from University of Wyoming, Professor Shima Parsa from the Rochester Institute of Technology, Professor Grigory Shapiro from the Federal University of Juiz de Fora, and Professor Aurora Gratmatikis from the chemistry department at PUC. So Nicolle, I thank all of the committee members for their time of reading and evaluating Nicolle's work. So Nicolle, you give your presentation that's going to be followed by questions and suggestions from the committee.
Thank you, Marcio. Hi, everyone. My name is Nicolle Lima, and I will present my PhD defense entitled Microscale Analysis of Foam Formation and Surfactant Alternating Gas Injection in Porous Media Micromodels. Water and gas are commonly injected in the reservoir to maintain the pressure and displace the oil toward production wells. And the amount of oil displaced is both a function of how well the reservoir is swept by the injected fluid and how well the oil is displaced in the pore scale, the residual saturation. When the secondary recovery becomes ineffective, we start to apply the enhanced oil recovery methods. The EOR methods are the applied techniques to maximize oil production through the interaction between the injected fluid and the rock oil system. Each EOR method will act in one or ideally both of these two factors. Different methods can be used with their own advantages and disadvantages. One of them is the gas flooding. When injected in the reservoir, the gas flows through the upper part of the reservoir, leaving a large amount of oil behind. This is called early breakthrough. Also, we have the formation of these instabilities, this viscous fingering. So, the idea here is to reduce the mobility of the displacing phase. And we can do that by alternating water and gas. In this case, in the water alternating gas case, we have a better sweep efficiency, but we still have oil remaining in the reservoir. In the third case, in the surfactant alternating gas case, first we inject a slug of surfactant solution, then we inject gas. In this case, we are forming foam inside the reservoir during gas injection. And foams are better injection fluids than aqueous solutions because they are less sensitive to gravity and permeability heterogeneities. And the success of foam as injection fluid highly depends on generation and stability of lamellae inside porous media. And foams are a potential solution to mitigate the adverse effects of gravity override, early breakthrough, reservoir heterogeneity, and viscous fingering on the sweep efficiency during gas injection. Foam can behave in different ways in the porous media. We can have a gas path, we can have the gas flowing, and for the discontinuous gas, we can have bubbles flowing. This is a bubble train, and also we can have gas trapped in bubbles. Foams are a two-phase system in which the gas is enclosed by a surfactant containing liquid film, the lamella. Also, the other structures of foam are the plateau borders and the nodes. Foam has high apparent viscosity by trapping gas in bubbles, reducing the flowing fraction of gas, and providing capillary resistance. So the idea here is to reduce the mobility ratio, and we can do that by reducing the relative permeability of the displacing phase and increasing the viscosity. Here, what we have is a three-dimensional foam. But when the foam is enclosed by the geometry, what we have is a line. Here, we can see the liquid film, the lamella, and the two plateau borders connecting the lamella to the pore walls. And on letter B, we can see the lamella flowing from 1 to 7 inside the pore body. In addition to the resistance provided by the presence of this lamella, the drag of moving bubbles along the pore body imparts an additional viscous resistance. And the important parameters involved here are the lamellae number and the lamellae velocity. We are going to focus on the lamellae number. The image on the right shows the mechanism of that affect apparent viscosity of foam. On top, what we can see is that the presence of liquid between the bubbles here is responsible for creating the resistance against flow. In the middle, what we have is the interface deformation because of the viscous and capillary forces that are a function of the flow rate. And in the bottom, we can see the surface tension gradient. So the surfactant depleted from the front accumulates at the back of the bubble, and then it slows down the motion of the bubble. The foam can be generated in different types in the oil industry. We can have a preformed foam. In this case, the foam is generated outside the reservoir. We can have a co-injection foam. In this case, we inject at the same time the surfactant solution and the gas. And in the third case, the surfactant alternating gas, we alternate the injection of surfactant solution and gas. And during this process, we are forming foam inside the reservoir. Regardless of whether bubbles are generated outside or in situ, the porous media molds and reshapes them. Now, the literature review. In 1958, Bond and Holbrook were the first to show that foam generated in the oil reservoir by consecutive injection of surfactant solution and gas could increase sweep efficiency. And they described their invention in a patent. In 1964, Bernard and Home studied foam properties using consolidated and unconsolidated sands and concluded that foam effectively reduces the permeability of porous media to gas. Here we can see the gas permeability curve. We can see that we have a low gas permeability when we have foam, compared with the case without foam. They varied the surfactant concentration, pressure, and the porous media properties. In 1994, Kovcek and Radke compiled all the information available on foam generation, destruction, and transport mechanisms in a really interesting work. Here on the left, we can see one example of foam formation mechanism called snap-off. In letter A here, we can see a gas finger entering a throat that was filled with the wetting liquid. At this time, the curvature and local capillary pressure rises to the equilibrium value. On B, we can see that when the bubble goes to the pore body, the curvature and the local capillary pressure falls with the expansion of this interface. At this time, we have a gradient in the liquid phase that goes from the pore body to the pore throat, accumulates here as a color, and then detaches the bubble. On the right, we can see how foam behaves in a porous media. We can have a continuous gas channel, the gas trapped here in bubbles, and the liquid films. In 2002, two works were published at the same journal, and both studied foam generation in homogeneous porous media. The idea was to correlate the minimum pressure gradient, that is the pressure enough to form foam, to form strong foam. And for goglets, the minimum pressure gradient scales with 1/K, And for Tanzil, it scales with 1/√K. The difference between these values could be explained by that they use a different surfactant solution, different experimental conditions, and one did the measurements during the transient regime, and the other one waited until the steady state. In 2014, in the Lisa Biswal group, they visualized oil displacement with foam in a microfluidic device with permeability contrast. Here is the porous media. So foam was pre-generated using a flow focusing device. Then this foam was injected in this micro model that was saturated with oil dyed in red color. Foam first goes to the high permeability zone, blocks this area, and then diverts the gas to the low permeability region here. In 2018, Kamal and collaborators evaluated the surfactant type and concentration in gas sequestration efficiency. To do that, they used core flooding systems here. And when they increased the concentration of the surfactant, they saw a huge increase in the pressure. This is the orange curve, the higher concentration case. In 2020, Wang did a micro-scale visual investigation of water alternating gas injection. Here is the device that they used. The oil was dyed in yellow, the water in blue, and the gas remained transparent. And they concluded that the multiphase flow was influenced by the pore throat morphology, the wettability, and the injections parameters, like the injection rate and the water-gas ratio. Another work published at the same year studied the impact of adding nanoparticles to the surfactant solution on foam generation and stability. They used a micromodel made with glass by dolomite, and they added nanoparticles to the surfactant solution. They counted here the number of lamellae that was generated, and they also did the pressure measurements. Most of the studies that focused on porosity analysis, they are concentrated in preformed foam. In our case, we are going to form foam inside the reservoir during the gas injection. The surfactant concentration was studied before, but in core flooding systems that do not allow fully visualizing the dynamics. And the observation was conducted in other works, but not evaluating the surfactant concentration impact. So the goals here are to study foam generation during drainage of a surfactant solution by gas, and the oil displacement during SAG injection through a 2D porous media using a microfluidic system. Also visualize the pore scale phenomena and obtain microscopic information from the pore scale analysis that can be used to improve continuous model of foam formation and flow in porous media. And to do that, we're going to use a 2D micromodel made with glass by Micronit. Here is a picture of the micromodel, the sizes of the device. Here we have the inlet, the outlet, the glass pore structure. We have one buffer zone in the entrance and the other one in the outlet. Here are the properties of the micromodel, the pore volume, porosity, and permeability, and the size of the channels. Here, our biggest throat has around 250 micrometer, and the smallest around 12 micrometer. This work was divided in two parts. The first part is about foam formation during drainage of a surfactant solution by gas. To do that, we used this experimental setup that consists of a syringe pump, a gas-tight syringe filled with air, a pressure transducer to monitor the pressure during the gas injection, a micromodel, an inverted microscope, and a computer to do the image processing. And the materials used in this part We use a surfactant solution made of a mixture with water and the sodium dodecyl sulfate, that is an anionic surfactant. Here we can see the interfacial tension curve as a function of concentration. All these values plotted here were obtained when the interfacial tension was stabilized for each concentration. The critical micelle concentration for this solution was 0.47 grams per liter. And the surface tension above the CMC was around 34.4 millinewton per meter. Another important parameter to be considered here is the viscosity. So here we have a table of the viscosity for different surfactant concentrations that we used. We can see that when we increase the surfactant concentration, the viscosity slightly increases. And to do the experiments, first, we have to saturate the device with carbon dioxide to ensure a complete saturation of the liquid phase. Then we saturate the device with water or surfactant solution. We use different concentrations here for each experiment, a different concentration, and we inject 3,000 per volume. Then we inject gas at a constant volumetric flow rate equal to 1 or 2 milliliter per hour. We measure the pressure and visualize the flow dynamics. And then the gas injection was stopped when steady state was reached. This is the base case. It's pure water displacement by gas injection. Here we have the device. The device is saturated with water in this case, water dyed in red color. So we do not have surfactant this time. The flow rate is 1 milliliter per hour. This is a real-time video. So you're going to see the gas invading here, the micro model from the left. Then we are going to see the gas percolating the micro model. And gas will find a preferential path. And as gas finds this percolated path, we do not have any changes in the phases distribution. Now to calculate the amount of liquid phase that was left in the reservoir, we can do an image processing. The top images here correspond to the mask. So here the device was saturated with the aqueous phase. Then we use a grayscale mask. And then we have the binary mask. To do this binary mask, we have to use an ImageJ default threshold. And the same procedure was done for the images taken after the gas injection. So here is the original image, the grayscale image, and the binary image. And to calculate the percentage of aqueous phase that was left in the reservoir, in the porous media, we have to divide the black area in the binary image by the black area in the binary mask. For this case, for the pure water case, the amount of water that was left was around 70%. We can see that the gas forms this preferential path percolating the porous media from the inlet to the outlet. Here is the pressure behavior during the gas injection. We can see that the inlet pressure rises for a very short time and then falls quickly, stabilizing at the steady state. Now we are going to start to add surfactant to the aqueous phase. And we're going to see that surfactant completely changes the flow behavior inside the porous media. Here we are below the CMC. Here is the concentration. We have 0.5 times the CMC. We form a few lamellae here. We can see at the end of the porous media. And then we form two preferential paths, one here and the other one here. The inlet pressure, the behavior here, we have this gray curve. So the pressure rises a little bit, then stabilizes at this plateau, that is higher than the one obtained with pure water. That means that we increased the flow resistance in this case. Now I'm going to show you a video. At this time, the micromodel was saturated with surfactant solution. The concentration was one time the CMC. We are at the CMC now. The flow rate is the same. And now this video is 4 times faster than real time. You're going to see the gas invading the micromodel from the left. The gas percolates the micromodel, and what we are seeing now, like you can see now, is that we are forming foam. So we are forming foam inside the reservoir. Because of the geometry here, you can see that we have all these bubbles formed. At the end of the gas injection, this is the phase distribution that we have. We only have 8% of surfactant solution left in the porous media. We can see many more lamellae was generated. The pressure behavior. This case is this light green curve. You can see that the pressure increases for a long time, finds its maximum around 20 minutes, and then decreases before reaching this plateau. When we increase the concentration, here, this dark green curve, this one here, we have 3 times the CMC, and we can see that as we increase the concentration, we also increase the maximum pressure and stabilize at the same plateau. Now we are going to see a case in which 30 times the CMC was added to the aqueous phase. The same flow rate was used here. This video is 16 times faster than real time. We can also see foam formation. And at this time, we have enough surfactant concentration to stabilize many more lamellae. So you're going to see that we keep forming lamellae during the whole experiment. And at the end of the test, here I will put in the end of the video, the gas found a percolated path, and the whole device is saturated with gas. We only have liquid present in lamella form. So here we have all the pressure behaviors for all the concentrations as a function of time. The video that I just shown is this dark red curve here, this maximum pressure. We can see that as we increase the concentration, we are also increasing the maximum pressure. For these cases, all these cases that we are above the CMC, we have the same interfacial tension, but we have completely different behaviors in the pressure. Another interesting thing is that we have the same slope for all curves, and the pressure rises as we are generating new bubbles. And when we are not forming lamellae anymore, we have a pressure drop here. All these curves, we have the pressure drop, and the pressure stabilized in 2 different plateaus. One possible explanation for the existence of these 2 plateaus is the thickness of the lamellae that were formed. So we believe that when we have higher concentrations, in these cases here, we are forming more lamellae, and we have enough surfactant to stabilize even thinner lamellae. So in this case, we have thinner lamellae, and then we have a lower resistance to flow. Here's an image showing the picture after the gas injection. The gas percolated the micromodel, and we can see the path taken by the gas at the end of the experiment. This path was digitally colored in red. The maximum pressure. We can see that we have a gradual increase in the normalized pressure with surfactant concentration. In the beginning, we can see a sharp increase in the maximum pressure. The maximum pressure stabilizes a little bit, then starts to increase again as a function of concentration. And the same trend was observed for the time for maximum pressure, the time when this maximum pressure happens. So we have a sharp increase, and it's a function of surfactant concentration. Here we can see the normalized pressure at the steady state. That's two plateaus that were identified. So below the CMC, these two cases here, we are at the lower plateau, and the pressure, normalized pressure, stabilized around minus 0.8, minus 0.5. At the CMC and near the CMC, we stabilize at 0. And above the CMC, for higher concentrations, we stabilize at the lower plateau again. In addition to the pressure measurements, we also could identify all the foam formation mechanisms. The first foam formation mechanism is called leave behind. In this case, we have the gas invading the pore body from two different places. So here we can see the yellow bubble. The yellow bubble goes through this body. And then we have the formation of these two new lamellae. These two we call leave behind lamellae. Another foam formation mechanism, the lamella division. In this case, we have a moving lamella. This moving lamella finds a post or a branching point and then divides into two new lamellae, the green and the blue ones here in letter B. The third mechanism, I talked about it before. It's the snap off. We have an original bubble here in red. This bubble goes through the throat. We have a gradient in the liquid phase. The liquid goes from the pore body to the pore throat and then detaches the bubble. So we are creating this new bubble, this blue one. The fourth foam formation mechanism is the pinch-off mechanism. In this case, we have a bubble squeezing another bubble against a post. So here in A, we can see that this yellow bubble squeezes the red against this post, and then we are creating a new bubble, this blue one. Concerning the foam destruction mechanism, we have the coarsening. In this case, we have gas diffusion from the small bubbles to the larger bubbles due to the pressure difference. So large bubbles grow at the expense of the smaller ones. This is how liquid fraction evolves with time during the experiment. So in the beginning of the experiment, we have a higher liquid fraction. We have what we call wet foam. And when the bubble loses its rigidity, we have the bubbly liquid, here, this really rounded shaped bubbles. And at the end of the experiment, we have a lower liquid fraction. We are here in this case. We have what we call dry foam. And in dry foam, foam has this polyhedra shape with curved faces at the edges. To further study the flow dynamics, we decided to count the number of lamellae and correlate that with the pressure behavior. To do that, we analyzed this yellow square during a video. To do that, we have to use an ImageJ processing tool. The first input is an image with device completely saturated with air. This is our matrix. Then we use a threshold to make the binary image. The second input is the device saturated with lamellae, so we can see all these liquid films here. We also use the binary image, and then when we subtract one image from the other, we can identify lamellae. All these red lines here. We have to make further steps to quantify them. For example, we have to divide multiple lamellae. Here we can see two curves. The blue one is the pressure, And the orange one is the lamellae density, is the number of lamellae per millimeter square. In this example, we have 6 times the CMC, and the flow rate, the gas flow rate was 1 milliliter per hour. We can see in the beginning that we have a sharp increase in the lamellae density. Then this value stabilized a little bit. And when the pressure was around 4, we start to increase the lamellae density, the number of lamellae again, reaching a maximum here around 21. And then we have a decrease at the same time as we have this drop in the pressure. And at the steady state, we have a constant value both for the pressure and for lamellae density. Here we have all the concentrations. We have the lamellae density as a function of time. We can see the same behavior that I shown before. In the beginning, all curves, we can see this sharp increase in the lamellae number. We stabilize this, then we have another 1 or 2 peaks here. And what we can see is that when we have the higher concentration, we also have the larger number of lamellae, the higher lamellae density, as shown here. So when we increase the concentration, we are increasing the number of lamellae that can be created. Now comparing the analysis that was done before for that yellow square, now we are going to analyze the whole device. And this analysis was conducted at the end of the experiment when we reached the steady state. So here is the whole device filled with lamellae. We divided the micromodel in 4 parts, okay, 1, 2, 3, and 4. And then we have here the total lamellae number for each concentration. The total lamellae number was around 2,000 and 2,400. And what we can observe is that in the yellow region, this region here, that it's the final portion of the micromodel closer to the exit, we have a higher concentration of lamellae. And the explanation for that is that all the lamellae that was created here in the beginning of the device, because of the geometry, this lamellae divides again. So we have a higher concentration here in the exit of the device. Another analysis that was conducted was to study the effect of the injection flow rate. Here we have 3 concentrations and 2 different gas flow rates. These continuous lines here were the experiments conducted at 1 milliliter per hour, and these dotted curves here were the experiments conducted at 2 milliliters per hour. What we can see from this plot is that the maximum value for the pressure is around the same when we have the same concentrations here. But the time that takes for this maximum pressure to happen, it happens earlier in the higher flow rate case. Another thing is that the steady state, the pressure at the steady state also stabilizes at the same value for different flow rates. So increasing the flow rate accelerates the evolution towards the steady state. And another interesting thing is that when we double the flow rate, also we double the pressure in the beginning of the experiment when we are starting to inject gas. The conclusions for this first part was that thin liquid films formed create resistance to flow, increasing the magnitude of the viscous forces against capillary forces. A pressure behavior does not depend only on the surface tension, and at higher concentrations, more lamellae can be created, and a higher resistance is imposed to the gas flow, represented by the increase in the pressure gradient. The flow resistance and consequently the inlet pressure is directly associated with the number of lamellae formed in the pore space. Now, the second part of my work is about the oil displacement by surfactant alternating gas injection. This is the experimental setup used for these experiments. Consists of a syringe pump, a gas-tight syringe to inject the fluids that here were the gas and the aqueous phase, a pressure transducer to monitor the pressure during the gas injection. The micromodel was the same. Here we used the stereoscopic microscope with a reduction lens of 0.5 times and a computer to do the image processing. This reduction lens was added so we can see the whole device during the experiment. First, we have to saturate the device with the oil, the Draciol 7, dyed in brown color. Then we inject 15 per volume of the aqueous phase. That can be water or a surfactant solution with different concentrations. Both are dyed in red color. Here, we only injected 15 per volume of the aqueous phase to guarantee that we will have oil enough to do the gas injection. And the flow rate used was 0.1 milliliters per hour. Here are the capillary numbers for water and for surfactant solution. Then we inject gas at a constant volumetric flow rate, here equals to 2 milliliters per hour. We use this flow rate to guarantee that we are forming foam. Measure the pressure during gas injection and visualize flow dynamics. The materials used in this part, we used the light mineral oil, the Draciol 7. Here are the density and the viscosity of this oil. The surfactant solution was the same as the previous experiment. Here is how the two phases look after we used the dyes. The interfacial tension as a function of time, we can see that for oil and surfactant solution, the values stabilize around 4 millinewton per meter. Here we can see a table with all the interfacial tension values, so all the combinations. You can have the value for air and water with dye, air and surfactant solution, air and oil with surfactant solution. Here, it's a video 16 times faster than real time. The device was first saturated with oil, here dyed in brown color. Then we inject water. So here the aqueous phase was water. This is the base case, so it's pure water. We have no surfactant added to the water. Now you're going to see the gas being injected on the left. The flow rate here, the gas flow rate, was 2 milliliters per hour. We can see that the gas percolated the micromodel. And when the gas percolates the micromodel, we do not have any changes in the phase distribution. Here on letter A, we can see a picture taken after water injection, and the amount of oil that remains in the porous media was 30%. And in letter B, in figure B, you can see the picture taken after gas injection. The amount of oil left here was 27%. We can see that the gas path taken, the path taken by the gas is through the water-filled pores. So the gas goes through the same path as the water. So we only displaced extra 3% of the oil. Here is the pressure behavior. So we can see that the pressure increases, finds a maximum, and then stabilizes at this plateau, at the steady state. Now we are going to start adding surfactant to the aqueous solution. In this case, we are at the CMC, so the interfacial tension is 34.4 millinewtons per meter. In figure A, we can see the image taken after surfactant solution injection. We can see that we have 32% of oil that was trapped here in brown. And then after gas injection, we have a very weak flow diversion. We only had extra 4% in the oil recovery. The pressure rises, finds a plateau, and then stabilizes at the steady state. Now we are going to add more surfactant to the aqueous phase. Here we have 13 times the CMC, and the flow rate is the same, 2 milliliters per hour. And this video is 16 times faster. You're going to see the gas being injected from the left. The gas finds a percolated path. But what else we have? We are creating foam here. You can see all these bubbles. So these bubbles that were created, they divert the gas. So the gas needs to find another path. And at the end of this experiment, this is what we have. In figure A, we have 30% of oil that remain trapped in the reservoir. And after gas injection, at this concentration, that it's 13 times the CMC, we only have 16% of oil remaining. So we saw that we noticed that we formed foam inside the micromodel during the gas injection. So the pressure increases much more than the experiment shown before, and then drops and stabilizes at the steady state. Now another video showing the gas injection in a micromodel that was saturated with oil, then displaced with surfactant solution at 30 times the CMC. Here the flow rate was 2 milliliters per hour, the same, and this video is 16 times faster. In this case, we have much more surfactant here, so we are generating much more foam. We can see here in the exit that we are producing oil. Here we are displacing the oil from the reservoir. And at the end of the experiment here, almost all the surfactant solution that was available inside the porous media was replaced by foam. Calculating the amount of liquid that was, the amount of oil that was present in the figure A. Here we can see that we only have 18%. Here we have less oil remaining because we are at a higher concentration. We think that we are near the steady state. For this case, we injected the same amount of surfactant solution, 15 per volume. And here on figure B, we can see that after the gas injection, we replaced almost all the surfactant solution by foam, and the amount of oil remaining was only 9%. So much more foam was formed inside the micromodel in this case, and the maximum normalized pressure here was higher. Now comparing the normalized pressure for all the concentrations, we can see that in all these three cases, we have the same interfacial tension, but we have different values for the pressure. So we have a higher maximum pressure for the higher concentration case. So high surfactant concentration leads to a higher injection pressure and a higher number of lamellae. That creates a stronger mobility control and more efficient oil displacement. Here's a table showing the concentration, the surfactant concentration. We are increasing the surfactant concentration here for all these three cases. As we are above the CMC, we have the same interfacial tension value, but we have a greater reduction in the case in which we have a higher concentration of surfactant. So my conclusions for this part was that for low surfactant concentrations near the CMC, gas flowed through the same pores occupied by the surfactant solution with very weak flow diversion. The lamellae that was formed was responsible for increasing the flow resistance, diverting gas to oil-filled pores and displacing the trapped oil. Even though the interfacial tension values above the CMC are the same, the higher amount of surfactant allows a greater number of lamellae to be created. For future work, I have a few suggestions to evaluate lamellae velocity during its formation, analyze the effect of surfactant type, and investigate the evolution of pore space geometry and wettability. I would like to thank you all for watching. I would like to thank the funding agencies, thank the committee for their time and willingness. A special thanks to Shima that helped me a lot during my stay at Harvard. A special thanks to Professor Sidney for helping me with the image processing. And thank you, Marcio, for all your support, help, and motivation during these years. Thank you.
Well, thank you, Nicolle, for your presentation. We'll start the questions by the committee. So I'll start. We have quite an international committee, so I'll start from the one that's probably located the furthest, from Professor Shima Parsa from Rochester Institute of Technology. I thank her again to participating in another committee from my group. So thank you a lot, Shima. Maybe that's the only advantage of this online life that we live now.
Yeah, we're very close now. So Nicolle, good job. Well, I have actually observed how hardworking you've been, so I was expecting a very good thesis from you. I do have some questions. Can you go to slide 22?
Sure. Do you want to see the video?
No, actually, this is 23, so I wrote it wrong, sorry. On the graph on 23, sorry.
This one?
Yes.
Okay.
So you explain the lower pressure for the higher concentration because we have, yes, at the end of the experiment, when it gets to plateau, you have lower pressure. And you explain it as if there are thinner lamella. That's why the pressure can drop below the values you get at CMC. Well, this doesn't really convince me. You also counted the number of lamellas. Is it like, did you see and you saw a different number?
Yeah, I saw a different number during the experiment. So the maximum lamellae number actually is higher for the higher concentration case. But at the end of the experiment, we have the same amount of lamellae in all cases. So let me show you the curve. So here we stabilize in all cases at the same amount of lamellae. So at the end of the experiment, the amount of lamellae is the same. During the experiment, I had a higher number, then I stabilized at the same amount.
Okay, so why would a thinner lamella create less pressure? Do they move faster? Because you observe these things. Do they move faster on the solid surfaces? Do they break up?
They are easier to break up because they're thinner. They create less resistance to the flow. So I have the same amount of lamellae in both cases. In both plateaus, I have the same amount of lamellae at the end. So I counted this multiple times. Even in the whole device, the measurements that I did in the whole device. So at the end, I have the same amount. But I think that I have a picture here showing I have a backup slide here with a different here. You can see that the color of the lamellae at the end is different. So here in a concentration, here you can see that there's the lines are black, and here we have like gray lines. Can you see that?
Yes.
So for me here, this lamellae, they're thinner than the ones here. So I think when we increase the concentration, we can stabilize thinner lamellae. So that's for me one possible explanation for that.
Maybe I'm not really familiar with foam enough to see how like the thickness is going to affect the final pressure. But do they move at the end when you're still
No, they're
injecting?
not moving at the end anymore. Here,
Let me
show you a video.
And let me throw one more thing to complicate the discussion, is that when we first saw these results, we thought that there would be different percolation paths. So the lower pressure would mean that we have more percolated path. And this was not the case. So sometimes in the lower pressure, we only have one percolated path. And in the higher pressure, we have more than one percolated path, which I cannot explain. I don't understand why.
Yeah, I have here the percolated paths too. So here in this case, we are at the higher plateau, and we have much more paths than in the one with the lower plateau. That for me is the opposite of natural thinking. I was expecting the opposite, that for the lower plateau I would have more paths.
In your skeletonizing the beginning before any lamella are there, does this look like a low resistance path compared to the 263 where you have? Could that be an explanation, that it just happens that it picked a low resistant path for this one? These, so in 64 where you have higher concentration, you have.
Yeah, this one here.
Yes.
What Tim is asking, if you go to slide 63, is by any chance this is a lower resistance path than this one?
Yeah, I don't think so.
We did like a numerical simulation of the single phase flow, and it doesn't look like there is any particular preferential path. It seems that it's very uniform, like the grain or the pore throat distribution.
Okay, so that cannot be. Well, this is a very complicated business.
Yeah.
Thank you. I think I have another question. So in 39 or 38 that you changed the flow rate.
This one.
Yes. Okay, so when you double the flow rate, technically the time should be half to reach them. Do they fall almost the same time if I divide the time for faster flow rates by 2?
If you divide the time that takes for to reach the steady state?
Yes.
Yeah, I don't know. I didn't calculate this relationship between the time. I know the values for the maximum pressure, for example, but I don't know if the time is related. But
Nicolle, if you make the time dimensionless with the flow rate, the slope is the same. So
yeah,
I think
this looks the same. I
they
added
scale
this
up with
plot
the flow rate.
in the thesis, the writing part.
Okay.
So I had a suggestion when I sent you a comments. I don't know if you received them, but
yeah, I received. Thank you.
What we're saying is that if you put this in terms of pore volumes injected, also is another way of normalizing this.
Yeah.
Do they overlap?
Yeah, it's a great idea.
Sorry for the interjection.
Yeah, well, yeah, it would be the same normalization. Yeah.
Yeah.
So in terms of what. I had a general comment at the beginning in your literature review. You showed us 2 different scaling: pressure scaling with inverse of the permeability, or the square root of the inverse of permeability. Is there any way that you can compare your results with either scaling?
I'm not sure because they used preformed foam. It's really hard to compare my work with other works because most of the works that were conducted in micro models, they used preformed foam instead of generating foam inside the porous media. So both of them were co-injection or preformed foam. So in that case that I shown before, the one with the minimum pressure gradient, right? Yeah, they used the preformed foam.
No, Nicolle, I think that, can you go back to your,
Yeah,
no, like
sure.
to the introduction
It's this
part?
one, right?
Yes, yes. No, they formed the.
Ah, okay. Yeah, sorry, I was confused. Yeah, I didn't try to make a relationship between this pressure gradient with the permeability, but it's a good idea. I can calculate that to see if there are a relationship. Do you think it's possible, Marcio?
We have one permeability only, so we cannot, we have only, we could try in different models, but we only have one for, or Nicolle ran the experiment only for a single device. And one thing is that it's like we in the plot where she showed the number of lamellae, so you have a very sharp increase in the very beginning, so but I think it's a different system because we have, in this case, they are co-injecting gas and liquid. And in our case, we are injecting gas in a saturated porous media. So we start forming lamella right away. So that's why in the number of lamellas, she showed like a very sharp increase and then a stabilization. So I don't know if we can directly compare, because in a sense, in these experiments, they are controlling the saturation of the gas phase with respect to the liquid phase. And in Nicolle's experiment, she's changing the saturation with time. And so I'm not sure if it would be easy to get some comparison or correlation with these experiments.
Okay, so fundamentally different experiments.
Yeah.
Thank you. I don't have any other questions, but I have comments on your thesis, which I sent you.
Okay, thank you very much. Shima, thanks again for participating in another thesis here in my group. Hopefully in the future, we'll get to bring you to visit us in Rio. So I'll move on to trying, I don't know who is further, Rochester or Wyoming, but going to Professor Vladimir Alvarado, and again, thanking him for participating in another committee in our group. And Vladimir has been a long-time collaborator. So thanks again, Vladimir, for your time.
My pleasure, thank you. And I don't think you should take a straight line from your location to where we are. If you remember coming here during a blizzard, it can take a lot longer.
Yeah.
Nicolle, so thank you. I enjoyed the presentation very much. I have a number of questions. So I'm going to start with something very basic. When you introduce the topic of foams, you refer to channeling and viscous fingering, almost like, a bit in a hurry. And so I'm going to connect that to something that I think you said. You said that essentially, if I translate correctly, the porous medium itself will generate the foam. The architecture of the foam depends on what porous medium you have, right? Is that correct?
The geometry of the porous media?
Yeah, the structure of the porous medium itself. So if I have something with a lot of polydispersity in pore size, that will generate a different foam than a very homogeneous packing of, spheres.
Yes.
Correct?
Correct.
So when you say, so I want to understand how you see the conformance for the different permeabilities, given that those different layers could be a very different, you know, disorderliness, you know, the more, you know, polydispersity in the distribution of pores. So would it, a medium with a lot of different pore sizes would, but, you know, larger permeability, would that generate more resistance than something that is a nice little pack of sand?
Yeah, I
Because
believe that's true. When you have like an homogeneous device, yeah, is that what you're saying?
More or less, yes.
Yeah, this is one example in which we have different, was a study conducted with different permeabilities. So in this case, when we have only water here, the gas flows to the middle here, in this channel. And when we have foam, foam first goes to this region here, the high permeability. So if in my case, as I have a really homogeneous, like a really homogeneous porous media, the behavior is different.
So in some sense, I'm trying to connect with a question that Shima asked you to try to explain that pressure response difference. And so I was wondering if the generation, I'm trying to connect two things, if the generation of the foam interrupts a particular path that is very permeable, then maybe, you know, when you combine that with having more tortuosity as the fluid moves through, what matters at the end is how much permeability is left for the displacing fluid, correct? And so if it's a channel that goes through a critical point, you know, where it's kind of narrow but not very narrow, and I have a different lamella, then that is going to tend to dominate your permeability to that fluid. So perhaps you don't need to look for a number of paths, but what that path is really like in the presence of that lamella. Do you follow what I'm saying?
Yeah, I understood.
So on top of this, if you actually calculate the tortuosity, if you have more tortuosity, you definitely have more resistance to flow because you have to go through more pores. It's like having a long pipe. You see what I mean? Rather than a short pipe.
Yeah,
so you need to think about what that restriction is to the flow, because if I just have to go around and around, it doesn't matter that you have a path. It might be
not the number of paths, but the
right. But what is
the way that takes for the gas to flow, right?
Right. And so it's not quite a question, but let me formulate it as a question. Do you think that would actually help to explain what you see in terms of pressure response?
Yeah, maybe. I think maybe it's a possible explanation because we do have a more tortuous path in these two cases that were in the high plateau, and the other ones that are in the lower plateau, I think we have less tortuous path. Maybe it's a good explanation for that. I
want you to think about it and maybe consider it in your review of your thesis. I wanted to ask you something specific. I think Marcia knows I have used microfluidic devices. We have collaborated with you looking at microfluidic devices, but there is something about the microfluidic device that can be misleading. Sometimes you have this narrow, shallow channel, and then the aspect ratio changes a lot because you're changing the size of the channels, but not the depth, right? So I want your best guess as to how do you think that height to width channel aspect ratio impact the foam formation mechanisms? This is a typical PhD question.
Okay. How the ratio impacts the foam formation, right?
Yeah. To give you some hints, I mean, your curvatures are very different in the direction you see from the direction you don't see.
Yeah, I can't see the curvature, right? Yeah, when we have like a really small throats, the curvature is really small, right? Yeah. Yeah, this relationship between like small throats and large throats, I think this adds to the one foam formation mechanism, the snap-off, is related to this ratio between the smaller throats and the big throats. And I think that this type of porous media that have all this different, it improves the foam formation. I think I'm forming more foam because I have this difference in this pore-throat relationship.
So I'm trying to tell you that I think if you look at the meniscus, it looks like a pancake in some of those pores, but it's not like a cylinder at all. It's like a pancake, you know, deforming through it. So I suspect that for some of these mechanisms, the width doesn't matter at all. You see what I'm trying to say? That it might be dominated by the other dimension. That doesn't mean it doesn't matter at all, really, but it means that what we think that is doing is not taking into account the other direction that imparts curvature to that meniscus, correct? So as you approach the size of the thickness, I think it looks more like a square, you know, pipe, right?
Yeah.
But as you get these pancakes, then I don't really know how, in some cases, this creation of new interfaces occurs. I think I can see how when you stretch it and it breaks, then I can see some of that. But I sometimes cannot tell if some of the, you know, sizes matter all that much. Do you follow what I'm saying? Because I'm trying to connect that with the size I can see, and I cannot always tell how the bubbles
You're saying about the other dimension that we can't see, right?
Right. So maybe you could make a brief comment in your thesis about that, you know, for people who are not used to seeing microfluidic devices. I want to move now to something that is, I made a comment in various places in your thesis, but I want to help you to understand what I meant by that. So what are the objectives of your research? You try to I try to isolate, you have two? Is that what you have, two objectives?
Yeah, I have two
You kind
objectives.
of put them together in chapter 2, which confused me. I tend to see that in chapter 1. But that's
chapter
okay.
1. Yeah,
Yeah,
it was in chapter 1, but then we changed a little bit the structure of the thesis. Then we were thinking, okay, let's talk about the literature review to say what is missing in the literature review, and then add the goal. It's the same that I did here in the presentation.
So what are the goals? I didn't quite see them in the presentation. I see them in the thesis. Okay. Do you have a slide with the goals?
Yeah, I have a slide with the goals. Maybe I was too fast in this part. Yeah, here.
Okay.
So my ideas here were to study the concentration during the foam formation. So I saw a lot of works in micromodels. Most of them were co-injection or preformed foam. So my idea was to generate foam inside a reservoir. And I choose this one because in the oil industry, it's easier if you alternate. You do not have a whole structure to produce foam in the platform. So you can just like add a slug of surfactant and then keep injecting gas. So that was my idea. And when I was looking in the literature, I didn't find any experiment in the micromodel doing surfactant alternating gas. So both the foam generation, varying the surfactant concentration, and the oil displacement using SAG, both were not. I didn't see anything in the literature.
You were more specific here on the slide than in the thesis.
I can use this sentence.
Well, and you had it in reverse order, if I remember correctly. But let me refine my question. So are you trying to demonstrate something, or you're telling me I'm going to study something? It's too unspecific.
No, I'm trying to demonstrate something.
Okay, that I like better. What
Okay.
are you trying to demonstrate?
Okay, because in most of the studies, people say, okay, I'm using this concentration. This concentration is above the CMC. They don't care about the amount of surfactant because as they are above the CMC, they have the same interfacial tension value. But what I'm trying to show here is that this amount of surfactant, the amount of surfactant that we are adding to the surfactant solution, it really matters. It's not a matter only on the surface. It's not a matter only on the interfacial tension. The amount of surfactant is important because during the gas injection, at one time I will produce a lot of lamellae because I have enough surfactant to do that. So here it's not the interfacial tension that it's counting. It's the.
So you have a hypothesis that is a goal, which is that you propose that the surfactant concentration impacts foam formation, in situ formation, right? In a surfactant alternating gas process.
Yeah, both in foam generation and inside injection.
Because you actually had the evidence. Because when you say study foam generation, what, as a function of permeability, as a function of temperature, as a function of what, I think what you just stated connects better with what I saw in the conclusions. And so, I mean, with all due respect, I enjoy what you presented, but I just wanted to connect because at some point I wasn't sure why you were doing some experiments. And then I don't like the verb to study something. Just, you could study something to death and not do anything.
Too general.
Yeah, and then visualize is even weaker. I think you want to visually demonstrate something or prove something or determine something. And so,
yeah, because all the experiments were conducted in core floodings. So you have the pressure behavior, you're assuming that you're forming foam, but you cannot see that foam that was formed.
So now that I'm not, I mean, your advisor will decide if those are the goals statements, but and between the two of you, I'm just suggesting that you reconsider stating them a bit different, well, a lot differently. Now let's go to why does the concentration of that surfactant affect this process? Have you considered the possibility that as you have formation of more and more micelles, your interfacial dynamics rheology might be affecting some of the foam formation mechanisms? Yeah,
the amount of micelles, I have more micelles in the lamellae, so I can divide more this lamella. So if I divide this lamella, I still have surfactant in the bulk to go to the interface. So during the experiment, I have lamellae with a lot of surfactant. So this allows me to divide these lamellae much more times because of the micelles that were present in the bulk. So this micelles goes to the interface. Each time we create a new lamella. So we create a lamella, the monomers goes to the interface, then we create another one. We still have monomers to go to the interface. And that's, for me, the explanation. The amount, we have a higher concentration, we have more surfactant to stabilize more lamellae.
All right, thank you. I'm gonna stop. I had another question, but I'm gonna stop because we don't want to be here forever, right? Thank you.
Thank you very much.
Thank you, Vladimir. I think your point on to be more specifics on the goals is perfect. So we'll talk to Nicolle, and then we'll probably incorporate that on the revised version. And I think it's a good idea to have that state directly in the goals of this study of the surfactant concentration. I think Nicolle explained well. The idea is that when you're measuring the CMC, in a sense, you have an infinite bulk. So you saturate your interface quickly. But now if you're forming in situ, you're generating more and more and more interface. So the point is that the CMC it's not really the important parameter to control everything. So thanks again for your contributions. And
I'm gonna move to a different place because there's a class here now.
Okay, yeah. So so finally getting to Brazil, but not to the state of Rio yet. I'll thank Grigory for again participating in Nicolle's committee. And Grigory, you have the word.
Okay, thank you, Marcio. Do you hear me?
Yes.
So thank you, Marcio. Thank you, Nicolle, for this kind invitation. I liked your thesis very much. So first of all, congratulations. It's really well-written text. And well, I mark a lot of things, but I will follow all the other members. I will send you just after our talk, after we speak now. And so I will just focus on some specific issues. So I'm from mathematical background, so I'm sorry, maybe some questions are a little bit naive, but still, I'm in a committee, I can ask them. So, well, in the introduction, I found a very nice introduction, but you don't cite literature, I don't know why, not in the introduction and also not in the literature review. So you make a lot of affirmative of statements about EOR methods, about trapped gas, percentage of trapped gas, WAG, SAG methods, and some places I marked just like, usually, at least in mathematics and engineering, all the statements in the thesis are yours or from someone. I don't think you can argue about like in the importance of foam EOR in engineering recovery, right? So maybe it's a good point to cite someone. Okay. Then in the section of literature reviews in chapter, so on page 24, well, it's just mathematical thing because you use phi for one thing, and then next you use phi for porosity. So usually we don't use the same letter, Greek letter, for different things in the same thesis. And well, page 25 in the figure 2.2, there is some error, but I marked it in the thesis. And then my question is on page 25. You explained, and you also explained in your presentation about 4 mechanisms of bubble creation. But I'm not an expert, of course, but I hear there are 5. And there is one mechanism that 2 bubbles squeeze another one. So you can squeeze the bubble against the wall, but you can squeeze 2 bubbles.
Okay.
And I can surely, you can find the literature. I can find it for you if you have any trouble.
Great, but this case would be from destruction, right?
No, from creation.
Oh,
from creation.
Okay. You're squeezing one against the other one. It's not the
2 bubbles, so no walls involved. So 2 bubbles squeezing, and then you divide 1 bubble into 2. And I think I saw it in at least 2 papers recently. So, but I'm not like, if you explain me that I'm wrong, I'm happy with that.
No, you can send me this work. I can add as another information.
Yeah, I'm not sure. So just one comment, because I think when we included the pinch off, like the pinch off, not necessarily was against a solid wall. So it's just a pinch off. So you're pinching off one bubble by another bubble. Okay, I'm not sure if somewhere in the text she said that specifically is against a solid the grain, but not. So maybe maybe these 2 things we are mentioning as a single mechanism. Maybe that's the point. But I'll make a point that Nicolle reviews this to make sure that's clear the process.
Okay, I'm happy to be wrong. And well,
no, it's not wrong. Maybe it's just a matter of how you classify different ways of classification. Yeah,
it's because I just find some papers about, I always see like, oh, before it was 3 mechanisms and then they discovered 2 and now that's 5 mechanisms.
Okay.
And then I read the thesis and there are 4. And now I'm lost because it was 3, 5 and now it's 4.
No, but if you can send this paper, that would be nice for us to put it together. Yes.
Okay. So another thing is on page 33. And well, this I'm sure I'm not wrong because I was working about it. So you are making a very nice review on this theory about how this stable the lamella is because of this theory. So that you have van der Waals forces and you have double air forces. So this is a really classical theory. It's called DLVO. It's not Derzhavin theory. It's given to 4 researchers. So one is Derzhavin, who you cite. Another is another Russian, Landau, and 2 Dutch people. So one is Verwey and another is Orvebeek. And so I just work with Hans Breuning. He's Dutch. So I mean, he would be really upset with you because you forgot all the Dutch guys. Okay. And the first paper, you're citing like 60 something. The first paper of Derzhavin and Landau is 41. So, and the second paper, Verwey Overbeek, is 48. And it's really easy to find. You just go to Wikipedia and call DLVO, and it's DLVO theory. So I think you put it absolutely correct, but just I think it's good to fix citations and names. So next, in chapter 4, I have a really naive question. So you measure really well the injection, so the pressure on injection, and you say that the outlet, it's just atmospheric pressure. But you have oscillations, small oscillation in atmospheric pressure. They do not influence the experiment? The
oscillation in the pressure or the oscillations in the lamella?
Yeah, you have oscillations in temperature, in the room temperature where you're measuring. So you probably, there is no influence at all.
I didn't understand. You're saying that I have an oscillation in the environment or oscillation in the plot?
No, so your outlet.
Yeah, it's open to the.
Just open to the room.
Yeah, right.
And the room changes constantly. So you have high temperatures in the morning. If you put an air conditioning, it changes. So, and these oscillations, you think they don't affect your experiment?
I don't think so. I did a lot of measurements, a lot of experiments at the same conditions and during the morning, during the afternoon, during different months. And I had the same behavior in the repeatability was good. So I don't know. I don't think the air conditioner normally is set at the same temperature, and I was doing the experiment in the same place in the room.
Okay.
I don't know if there's any...
No, I'm just asking.
Yeah,
so
I don't think so.
Then in all your pictures, for example, if we go to picture 4.10 in the thesis, you have it. I didn't wrote here which slide it is.
4.10, this one here.
Which one? Nicolle, we are not seeing your thesis.
No, okay.
You're sharing the other screen. You're sharing the PowerPoint.
Okay, sorry. Let me.
Yeah, let me also.
This happens a lot with Zoom. You can share something.
I think it's better for you to share the screen, not the window that you're working with.
Oh.
But then you just bring the thing to the top.
Yeah, or you can. Oh, okay. If it's easy, it's okay. Or you can just go with the slides. It's a pressure. It's a graphic pressure over time. So you have time on the horizontal and pressure on the vertical.
This one here.
Yeah, that's one. So usually in oil engineering, we put breakthrough time in all graphics like that, because like I try to understand from your video and it doesn't seem so. If it would be in core flood, this peak should be the breakthrough.
Yeah.
But it doesn't seem to when I saw your video. So now I'm a little bit lost. And maybe you can put, I don't know, this is a breakthrough?
Yeah, this is the big breakthrough.
Yeah, but so, and then it's another one. If you go, I think 417, and then you can, this one. And then you can see that when you add surfactant, it's quite smooth. There is no peak anymore.
Yeah, there's a really small peak here, but it's
so where is the breakthrough? So maybe it's a good point to add breakthrough to all figures in your thesis, just to make sure the reader understands what's going on. Because, and then the question, of course, it's, so with surfactant, you have earlier breakthrough or later breakthrough. So exactly this,
Yeah, this one. So here, in all these times we have the Oh, not the breakthrough. Yeah, sorry. This is when we find the percolated path.
Yeah, so not the breakthrough. So
Yeah,
it's really, I didn't understand, and I don't really understand the physics here. So it would be interesting to know if actually you already did the experiment. So you can just conclude something about the breakthrough time. So
yeah, I already have the time for each experiment. I already have the time that for the breakthrough. It's really easy to add like a line or a point, like mark the time when we have the breakthrough.
One important point, I don't know, that's not clear to me is that what is the breakthrough in the case that you have a surfactant solution? Because is the first point where some gas reaches the outlet, but it's not a percolated path?
Oh yeah, you're right.
So that's the point. So the percolated path is the maximum there. So you're
right.
already producing a lot of gas, but it's not a percolated path from the inlet to the outlet.
Yeah, you're right, Marcio. So it's only for the graphic where you don't have foam. So it's the first one. Yeah, you're right. And then might make sense, of course. Okay, then in the figure, it's your slide 23 again. And so my natural, I expect if you add more surfactant, at some point, it has to just stop making lamella. So this cannot grow forever, right?
Right.
I mean, and why you stopped at 15? I mean, at what point it stops growing? At some point, it should change the behavior.
Yeah, maybe I don't know the limit of adding surfactant. I thought like 30 times the CMC was a really high value for the concentration because I added a lot of surfactant. But maybe if I add even further, I would like generate more and more.
But it's not possible. I mean, when you have, like mathematically speaking, when you have pure surfactant, there is no lamella at all because there is no water to form.
Yeah, I have a theory. I was thinking about that the other day. Here in this total lamellin number, you can see that here that we have a maximum value at the exit here, and the values here were growing as we are increasing the concentration. All the values were around 600. I don't know if maybe in this region I would reach the 600 too. Maybe here have the same amount of lamella than in the other regions.
So what you're saying, actually 15 is quite close to the border.
Okay.
No, 15 is the highest concentration.
The highest concentration.
No, I say if you put 18 or 20 and then it stops forming anymore, then there is no effect. So somewhere there is a limit.
Yeah, there's a limit. Yeah, that's what I'm saying. Maybe the limit is like around 600 lamellae per region. Yeah.
No, I understand what you say. It's perfect because I didn't say any work about that. And actually we are working on modeling how surfactant influence, so how the concentration influence the foam displacement. And there is a lot of literature, so there is a lot of hypotheses. The most common one is that above CMC, nothing happens. So this is the today. So your thesis in this point, it's changing something. Because today, over CMC, there is no importance, no influence of surfactant in the models, in mathematical models on foam displacement. And you're saying, no, it's actually a lot of difference. But what I'm saying is, so what today models think about, for example, if you go into stars, what model is implemented in stars is that you reach CMC and then it's constant. What you're saying is not, it's still growing, but then you see that there is some constant anyway. So it should be really interesting, at least for me,
to find the limit.
If you know the limit, and then we can model something on that and use it in simulators.
Can I interject just to suggest one more thing, Nicolle? Think about finding a paper on the phase diagram of SDS, because it will not form. I mean, I can send you a paper I published about another surfactant, because as you increase the concentration of surfactant, you form more than spherical micelles. You start forming all kinds of structures in solution. So that can affect the rheology of the surfactant solution. So I can send you a paper. We threw at it everything, the wrench and the whole toolbox, trying to find that out.
Yeah, that's
and so
great.
It'll be good because there will be a limit that you could start forming liquid crystalline phases, and that starts changing how this fluid moves in the lamella. Sorry about the, I just want to, I don't want to forget about it.
Let me make a comment, Gregory, to see, I've discussed this with Nicolle some time ago, is that, I don't know if it makes sense to you or not. So what Nicolle is showing is that you have, probably there is a limit where you would have one lamella, so where you can correlate directly the geometry of the pore space with the number of lamella. So let's say in equilibrium, you would have one lamella for each pore throat or something like that. So maybe that would be the limit. So it in a sense, coming back to what Vladimir said, that should be the goal, and I agree with that. Because if you look at the literature, if it's above CMC, everything should be the same. People don't look at it. And then we always thought that this didn't make sense, because if you're forming more and more and more interface, what matters is the ratio of interface and volume of bulk that you have. So the CMC, in a sense, when you measure CMC on a tensiometer, you have an infinite bulk, and then you have a constant interface or area where that's very easy to saturate that area. So if you're forming an in situ emulsion, you're forming more and more interface. So it matters how much surfactant you have available to stabilize those new interfaces that you're creating. And I think there is a limit where there's no more points to form an interface. So I think if you, this is a completely a hypothesis with no verification at all. It's going to come to a point that if we increase more the surfactant, we are not going to form more lamella, because there's no nucleation sites or places to put those lamellas, and then that would be our limit. But I don't know. We would need to test that.
I perfectly agree with you. What I'm saying, just if you do more 2 experiments, let's say with 18 and with 25, maybe you can prove this limit exists.
Yeah,
and that will be something really new.
Mm-hmm. Yeah, that's a good suggestion. Yeah,
I mean, yeah. Okay. Well, and then, oh yeah, in chapter 5, you have this discussion about weak form and strong form. And then you show actually that so in this graphics of pressure, you can say you have this in a lot of pressures depending on surfactant concentration.
Yeah.
You show them, yeah, for example. So then you argue in your thesis that some of them are connected to weak form and some of them are connected to strong form. And there is this classical figure when we actually measure, so it's really recent, actually, it's not so old. You measure, you change the flow rate, so the FG or FW on the horizontal axis, and then you plot your apparent viscosity, and then you have a triangle. So we say that the left part of the triangle is weak form and right part is strong form. So you have a really classical division, what is weak form, what is strong form, just visually. And then I was wondering if there is some other type of, so you are studying different directions. So you are now just changing concentration. So the FW is the same. So the amount of liquid you are injecting is the same. So you are just adding one dimension to that plot. So maybe there is some change in behavior depending on concentration. I'm not sure it's trivial for you to plot, but then maybe you have a lot of data. So the point is plotting in some smart way this data, and maybe you can observe the behavior change. And this will actually make a lot of difference as well, because that plot was really classic and now it's everywhere. So if you just manage to add another dimension to that plot, it will be really nice scientifically.
Thank you very much.
Yeah, so that's, and well, and just a little joke, you start your thesis with in situ in late, so in italic, and I was like, wow, this is really nice thesis. And then no in situ, but after that was in italic, only this first one. So I was like, yeah, best written thesis ever, but then, yeah.
Sorry to disappoint you. I will correct all the in situ.
Yeah, That's okay. So congratulations, really nice thesis. So you see, we can actually talk later if you want. I think we have a really nice things to do after.
Thank you very much.
So congratulations again, Marcio.
Okay, thank you, Grigory. And yes, let's discuss more, I think, to see if we can connect the type of the models that you developed and see if the data that Nicolle generated can be used for the development of these models. We should do that more. So thanks again for your comments. I made notes of all the comments here, so we can incorporate that in the revised version. And so finally getting into the city of Rio de Janeiro, and I'll thank Aurora for participating again in another committee. And then we rely on Aurora a lot when we need to know anything in more detail about chemistry and understanding these things. So Aurora, thank you very much.
Thank you, Marcio, Sergio. Thank you, Nicolle. I really like reading the thesis, as you can imagine. I was all excited. I have to say that I was extremely excited when you invited me for the committee, but I only had time 3 days ago to read it. So I have to confess that. And that I'm apologizing right now because I would like even to have talked to you before this defense about some things, but I only got time to read it on the weekend. So that's what I'm apologizing
No problem.
ahead. I hope I can be quick, and the other things I can tell you later because I have a few comments that I hope can improve, of course, the thesis. I agree totally with Vladimir that was saying about the goals, and especially because when I see when I started reading, I also was kind of lost in that first chapter of introduction about the objective exactly. The second one gave me a better idea, but it's still, when you show here not the goals but the slide before the goals, which I think is slide 9, if you can show it. I was understanding better because it's really the gap in the literature is what you say. More studies are focused on that, and how surfactant concentration can impact is what Grigory is so interested. You see, you already got his interest on that because that there is a gap in the literature and in knowledge in that, and I saw like there, that's clearly what I saw then in the results, because I wasn't kind of matching what I saw in the introduction with the results. Say, well, she focused both on chapter 4 and 5 on effect of surfactant concentration on that. But then my first suggestion, and it's not a requirement, it's just a suggestion. It cannot even be for the thesis. It can be, I don't know, did you already publish this work?
No, not yet.
And then I suggest for the title of the paper and all that, I suggest that you include the words surfactant concentrations on those titles, because that is what is going to be the key factor in your research. Because if you just leave it like micro scale analysis and foam formation, and there are going to be a lot of those keywords in the literature. But when someone sees that you studied the effect of surfactant concentration on that, perhaps is going to become more interesting, and it goes more into your into the gap that you detected in the literature, and also then reformulate those goals to be more specific and point out at what you really want to show. And I think that you show some of that. That's just a suggestion. Once again, I know that changing titles of thesis is very complicated, so no need to do that now for this thesis, but at least for the paper, I will strongly suggest it. It's very interesting, that question also that was asked and you answered, that why most people say above CMC, but it's not what you saw, right? The first thing is that, as Marcio was mentioning before, what is more important in porous media is the number of lamella that are created. And it's the equilibrium actually, or the competition between lamella creation and destruction. Because you might create a lot of lamella and destroy it all over the time. So it's not just creating them. And then that's one thing that I saw written in some parts in the thesis, and I would like also to comment that reduction of surface tension or interfacial tension is not so important here. Of course, it's important not to have water that has a very high surface tension, but once you get to something below 40 millinewton per meter, it's not important anymore, because that allows you to create the lamella, but what you need the surfactant for, rather besides reducing surface tension, is to keep that lamella stable. So that competition between creating and destruction, the destruction cannot win over the creation, right? My internet is still on, right? Because I saw Nicolle frozen there, and so I don't know if it's me or it's her. It can happen. Nicolle is there? Listen?
Yeah, I'm here.
Okay, okay. Sorry. Is that, we that are used to teaching online, we know that sometimes you don't know if you're still connected with the students, right? And so here I'm always afraid of losing the connection. But then what I was saying is because that also has a lot to do with the surfactant. Surfactant is not only needed for creating the lamella, but it's very needed for keeping that lamella stable. And in that case, the surface tension is not so sometimes when you say, well, even when this and this and that have the same low surface tension, the behavior is different, that doesn't surprise me, because that's not what is impacting the destruction, right? Also, you have to just, I don't know if in some points you meant that, but the IFT that you have at the water-gas interface in the porous media is not related to the one that you see in the lab, right? Because here you're going to have a curvature and you're going to have a very small diameter, so the IFT is going to be much higher, right? And also the surfactant can decrease it more. But then when you look like at this point of the importance of the surfactant stabilizing that lamella, is when you understand better why you need a lot of surfactant. Not only you are creating, as Marcia say, a lot of more interfacial areas, so you're going to need a lot more of surfactant, and that's what the number of lamella is directly related to the concentration of surfactant. You put more surfactant, you're going to increase the number of lamella. And it doesn't matter if you are above CMC or below CMC, it's going to increase. You are like giving more fuel, right, to create that. But also because you have then the other stabilizing mechanisms, as is the Marangoni effect, the elasticity of that lamella that is needed for breaking through the pores. All those formation mechanisms really need an elastic interface. And for that, the type of surfactant and the amount of surfactant and the interaction between the surfactant molecules in those lamella are very important. So that also will make a difference. And I believe that in the case of SDS, that is going to be make more difference than increasing viscosity, for example, because it's not, if you have a polymer perhaps, but, or something that forms really elongated. It's true also that surfactants have like a second CMC, right, when you start forming this rod-like, but I don't know if you get, because you are using so much surfactant, relating that to, as you say, 30 times the CMC, perhaps you don't have 30 times the CMC in bulk anymore because you use so much surfactant for creating a new interfaces that you cannot consider the same that you consider in bulk, right? So that's the other thing. So that was the thing I wanted to start with, because I also have a lot of comments, but I'm only going to focus on the ones that I really I can discuss with you better, and the others I can tell you later. Well, already talk about those lamella stabilizing mechanisms, and even there is an interesting thing, at least for bulk foam, that when you have very high surfactant concentration, it actually is bad for foam stability, because the Marangoni effect is reduced, because you don't have any more resilience, the surfactant going into that gradient of surface tension, because you get you supply the surfactant for reducing surface tension from the deformed areas from the book, because you have so much surfactant in book. So it kinds of it jeopardizes the attempts against the stability. But that is more for book than in porous media, but it might be a fact as well. So I think you have to focus in that increasing surfactant concentration increases number of lamella, because you have more surfactant available to form new interfaces. And of course, it will have a limit. And if you increase too much the surfactant, then you can even have precipitation and absorption and other effects as well. So it's not good to use like very high concentrations of surfactant, even if you assume that it's going to form a lot of lamella. So there is also in there. I only have one comment in terms of formatting, that is, you mentioned in page 37, when you started talking about the CBF and the NBF, the black films, you have that graph 2.16. And then you mentioned, and then you explain what is the two types of films and some details on the disjoining pressure even. And then you mentioned again in the other part, when I think, before that, sorry, in figure 2.14, you already mentioned all that. What is the CBF and the NBF? So I think you repeated the concepts, some of the concepts in both graphs. So perhaps it's just take a look at that and see. I know that you first are talking about porous media, and then you go to foam in general, drainage and stability, but it's because I thought that was like repeating the whole same thing. Perhaps you can do that better. And then now I go to the most, I'm running here because I'm the last one to talk. So I'm always like, oh, we're going to be late because of me, but I want to talk about this. So I'm always the late in Marcy's committees, because I'm the one from PUC, so I don't get to talk a lot. That's a good strategy from Marcy, because I talk a lot usually. But I really want to discuss with you the surfactant. So if you go to, and now I'm going to need this thesis, if you can put it in there, because I don't think you're showing here figure 3.3, which is the air-water interfacial tension. If you can, please.
Let me share the screen again.
Since you mentioned that you haven't published yet, then I'm trying to help here before you publish some things that I would like to point out.
The thesis?
Yes, it's
Which
okay.
page?
It's page 47. Yes, so you see, that's a typical graph for me of either contaminated water or a not clean enough cubit for the tensiometer, because water, especially if it's with that conductivity that you're showing there, I assume it's milli K, because it's very low conductivity. Water surface tension is 72.5 or around that point. It cannot be 62.
In this case, we added dye to the water.
But you added dye to the water when you measure the interfacial tension?
Yeah.
Because what you have in there is a typical, like you see, water will never reduce the surface tension. That will be the dye in the water. So then in that case, you need to specify that, because the way you say is that the equilibrium surface tension of the water is 59.7.
Yeah, here.
So if you added the dye, because for me it wasn't clear at which point you added the dye. I think it's important. If even I will say, if you don't need that, as I don't think you need it, at least in this case, but that can make a a bit of difference. If you don't need that, I wouldn't even show it because it's just bringing a question that why do you have a water that
has a lower
reduces,
interpretation than
and
expected.
it takes more than 2 hours to stabilize it. Like it doesn't make any sense in my head. It has some contaminants, that's what I was saying. But if it is the dye, it means that the dye is a little bit surface active. And depending on the concentration of the dye, it can also be affecting the stability of the not the stability, the surface tension curve of the surfactant. And then we go to that, now is the 49, yes, that. So that's a typical surface tension curve for SDS with impurities. Of course, you have a 90%, that's known. I still don't think there are a lot of impurities. I don't think there is like 10% of usually the impurity that affects most is the dodecanol, the alcohol, the decyl alcohol that comes from the hydrolysis of the SDS. And it affects because it is much more hydrophobic and therefore it absorbs faster at the interface than the SDS. And what happens is once it goes down, and then once you keep adding SDS, you start forming some micelles, and then the dodecanol migrates to the micelles, and then the surface is saturated with SDS again, and that's why the surface tension increases a bit. What I have read, and I can also send you the paper later about this type of commercial surfactants. I'm not even thinking about the dye here, which could also be affecting that. But I'm not thinking about that because I didn't. I wasn't certain if of the concentration of the dye was going to influence a lot. But you can do the same curve without the dye, and then you will have the answer for that. That's easier than taking out the impurities. But when you have commercial surfactants with impurities, usually you don't, the recommendation in the literature is not to get the CMC from that peak bottom thing, because it's not really at that point, you don't have micelles in great quantity. You cannot ensure you're going to have saturated interface. Let's put it that way. That is what the CMC is usually taking at. So usually it's taking, there is another parameter called dissociation concentration that it means the opposite. You go to the end of that line when you're ready, you guarantee that you have the micelles of SDS, and then you go down. And the point when the surface tension start going down means that is the moment, is the concentration at which you start losing your micelles of SDS, right? Because then the dodecanol is going to the interface and messing with everything. And that should be the point taken as CMC, which is not, is called like that. And look, if it was just a characterization for your system, I wouldn't even mention it here because I say, well, you can call it any way and take the point you want. But what happened to me when I started reading is that after I realized that, and I look at that and say, well, for me, it would be something between 1.5 and 2, that CMC that is recommended to take. Then all your results started making sense. Because if you start looking now at all the graphs, for example, if you go to, that I separated into 2. If you go to page, what can be the graph? That graph that everybody has been discussing, slide 23, I think, is page 66. You can go to page 66. Here. If you look at that without looking at the concentration and not knowing where the CMC is, for me, there is an obvious trend for the 3 green ones, and then the blue one changes the trend. Now you go to see concentrations, and the green one is 1.18, 1.55, and the blue one is 3.1. So exactly where I tell you that should be your CMC. And CMC might not seem important, and I understand for lamellas and all that, but CMC is important because you need to be at least above CMC to get some good results. And you can see that also that correlates with the lower pressure. The blue one is the one that goes all the way down, while the green ones, which you are below CMC, actually, in my opinion, of course, you still are above. So you have different trends, and that makes more sense for me. So you can see from, that's what I say, I don't want to delay the defense, but if we go like every graph, like you go the next one, 4.21, you're gonna see it looks like the blue point is the 3.1. So CMC is between the green and the blue. That's when you start getting something. Forget about the 15.5, which I think is a very, very high concentration. It's like 10 times, which it's not 30, it will be something around 10 times CMC, but 10 times is a lot, right? But you see the other ones are almost stable. So that means
plateau.
Even when the number of lamella can increase, you can see a behavior that is more, while the other one is increasing because actually below CMC, you have not enough surfactant to have something. And you can see the same in the other one that talks about the time. It's even more obvious that after the blue one, then you have a different slope. If you go to 4.23, that's what I was apologizing at the beginning because I only realized that almost yesterday when I was reading. So you see the blue, you go green, 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 and blue stops and then stabilizes. So I suggest you to rethink about the CMC that you are reporting. And I can send you the paper. It's quite an old paper, but there are other papers more recent that explain very well why in commercial surfactants like that one with 90%, you can see that. Because then you will have to rewrite some of the explanation. You cannot call it anymore below CMC, above CMC, but I think it will make so much more sense. Even when I was looking, when Shima was talking about the one that only have like 2 preferentials or 2 percolations, I think pass, that was 3.1 exactly. I was like here, like, oh God. It's so easy to explain when you consider that the CMC is between 1.5 and 3.1. If you will have salts in there, I will believe that the CMC was lower because salts will reduce CMC, but you don't have any salts in here. Then as I say, for me, then every graph as you go from there, I will have you an explanation based on that. And but what is also important is that the other thing is when you mention the thinner lamella that you can observe in the very high concentrations, it might has to do with what I was mentioning at the beginning, very high concentrations. Even if you have a large number of lamella, it can weaken the elasticity of the film because the Marangoni effect it doesn't work so well when the gradient of surface tension is not resolved by the surfactant that is in the lamella and not the one that is in the book. And it comes from the book. Imagine like elasticity, it goes like this, and the surfactant make it come back. But if it comes from the book, it just keeps like this way. It doesn't need to go back, and that can weaken, and that can make it thinner, that lamella. And also because of that, you get a lot of destruction of lamella, and then you don't get. That's what is interesting, that you can see number of lamella keeps increasing. But that depends also on how you manipulate that graph 4.30, that you have when you count the number of lamella, because it has several peaks, right? So it's true that the one, for example, 15.5 has a peak, but it also has a first peak. Before that is at the same, and the same with the red line with the
and then we're decreasing the number of
so those two, on those two higher concentration, you have 2 distributions, or not distribution, I'm thinking but 2 peaks, right? I will stay with the first one, that is the one that you can compare with the others, and you will see it is stabilized, it doesn't increase anymore. And it actually happens if you look again after 3.1, and you can see the green ones either go very low, and so you see between the green and the blue is that you start getting that increase in there. But even when you have some increase, increase that is more or less, right? Because between like 24, I will say that up to 6.2, which is twice the CMC in my calculation, or three times the CMC. Up to there, you have a real, you have like something stabilizing. After that, you have like very, two concentrations are too far away one from the other as to have a trend, right? But the important thing is, even when you have that, when you calculate for each section of the micromodel, you see that it almost, if you go to the one that is with colors, very nice one, the next one.
Which one?
4.33, the figure. That one. You can see that it goes 1.18, 1.55, 2.36, and then I would say that it's 3.1, it kind of stabilizes. It doesn't increase as much more. And CMC is not the key. It's not the only parameter to look at, but you definitely need to be above the CMC to have something more stable, right? But it will be a combination of the CMC with the number of lamella that you can generate in the porous media. But it's that equilibrium between the formation and breaking the lamella, right? So I already talked about this. So other than that, it's just I really think you can have much powerful conclusions with that analysis, and you can really bring about the importance of surfactant concentration without needing to enter in a lot of chemistry there. But I think that understanding those points that I just mentioned now can, I hope it can contribute to the thesis. That's it. Thank you very much for the patience.
Thank you very much for all your comments. You were great.
Well, thank you, Aurora. I think it was really helpful, this analysis of the CMC, and it really does make sense. The cutoff of all the behavior was in that around that 2 grams per liter. So I think it was a very important point for you to bring this up. Thanks. So with that, I open the floor to any question that someone wants to ask from the audience. Okay, so if nobody wants to ask any question, I will stop the recording here.